Hello, my name is Pedram Majarad, and today I want to talk to you about non-destructive testing. There are a number of non-destructive testing out there, and depending on what we're looking for, there might be a few options to use. Talking about non-destructive testing, their applications, different types, and limitations will take longer than one presentation. So I'd like to introduce to you a few of them in this presentation today and promise to come back and introduce more later on. In today's presentation, I'll try to introduce a few that are used widely these days in Australia. There is a law of fives for concrete repair and rehabilitation. I'm sure most of you have heard of that, and you understand that the later we rectify the problems within the concrete structure, the more expensive they will cost at the end. So if we get to diagnose them, see them, and monitor them in the first place, we only need to spend less money than at the very end to repair and replacement after generalized corrosion or deterioration. In this chart that you see now, testing and monitoring can come into play at the very beginning or any time in this chart, but obviously the sooner the better. In the next few slides, you can see some photos that are examples of where testing could prevent these situations or at least help identify the root causes of these problems. How do we test concrete? Yes, the concrete can be tested in fresh state, meaning when it is still in fresh or plastic stage, or at hardened stage. But either way, the testing will be categorized as one of these non-destructive, semi-destructive, or destructive. For non-destructive, that we will talk about later, a bit later today. But for destructive part, it is mainly lab testing on samples taken from concrete, such as coring. And we also have semi-destructive testing in the middle, because for these tests, you will need either a small sample, like ground powders or etc. of the concrete, or need to cut a small piece of concrete or drill into that. So it's not completely destructive, it is only semi-destructive. We will have to talk about some of these semi-destructive methods as well in our talk today, because they're really related to non-destructive testing in general. But what is actually non-destructive testing? Non-destructive tests are those inspections, tests, or evaluations of materials, components, or assemblies without abolishing their serviceability, meaning that you won't need to take core samples, or you won't need to stop the operation of the structure while you're testing its concrete. Or they can be done with minimum damage to the concrete, especially when we're talking about semi-destructive tests. Non-destructive testing determines the quality and integrity of materials, components, or assemblies without affecting their ability to perform their intended functions. Also, they can be done very cheap and very fast, generally faster than most lab tests. And add to that, there is no need for sampling or coring as well. Non-destructive testing is a very simple process, and many repeat tests can be performed on concrete, whereas you don't have this luxury with destructive or coring of samples. Where do we use non-destructive testing and when? It can be done at any stage of concrete life cycle, from QC during placement or after final set, or all the way up to forensic investigations where something has gone wrong. But this is very important to notice. Non-destructive testing has its own merits as well as its limitations. These are just tests, and like any other test, there is a definition behind that. Even a simple F'(C), aka 28-day compressive strength of concrete, doesn't really give you the strength of concrete at any point of that concrete element or at any time of that. The number will only give you an idea of the strength of concrete based on a test done with so many boundary limitations and definitions, percentile, and all other factors here. So this is really important to understand, that we only get some ideas from each test, and it can also apply to non-destructive testing. Non-destructive results can sometimes be ambiguous, and direct observation like coring of the concrete may be necessary to confirm or verify the non-destructive test results. In practice, the combined use of 2 or more NDT techniques would provide a more comprehensive information and result in a more reliable diagnosis. Most techniques require a high level of expertise to interpret the results, and operators generally should have considerable training in the use of equipment and in condition assessment of concrete structures. What we usually get out of NDT, probably you know more about the strength, mainly from the surface or sometimes from inside. It could be tensile, pull-off, pull-out, or compressive strength. Density, modulus of elasticity, cracks and void detection, placement quality, rebar location and cover measurement, surface absorption, electrical resistivity, and also corrosion potential, and many other things. And these are being done using different methodologies and techniques. And the good news is, like some other industries, this NDT in this industry is a fast changing one, and new products and technologies come to the marketplace every day. And in terms of methodologies or techniques used, I could probably name a few of them. Visual inspection is very important. Surface hardness, ultrasonic pulse velocity, permeability testing, penetration resistance, radiographic, sonic methods, thermographic, and ground penetrating radar, infrared technology. These are the things that are being used widely these days. It is fair to say that the first non-destructive assessment is the visual inspection. Obviously, visual inspection is easy and fast to do and gives a fairly good understanding of the structure. Although it needs some experience, but it is always the first step of on-site assessment. What you can find out from visual inspection is like cracks, their dimensions, spalling, color change, weathering, stains, efflorescence, lack of uniformity, honeycombs, bleed marks, and many other things. Never underestimate the importance of visual inspection, because it can give you a lot of ideas of what testing is required in the next steps, and it can give you a good understanding of the condition of the concrete at that stage. Another well-known non-destructive testing is rebound hammer. Rebound hammer, such as Schmidt hammer, is a simple device that is used to measure the hardness and quote-unquote predict the strength of concrete. This is a spring-loaded impacting device that incorporates a scale to measure the energy of the rebound following the impact. The extent of rebound gives an indication of the strength of the concrete at the surface position that it is tested. A minimum 10 impacts would give an approximate indication as to the compressive strength of concrete at that location. The device is very, very sensitive to a number of factors, such as the surface finish, aggregate or mortar exposure at that location of concrete, the moisture content and hardness, and these factors can influence the predicted strength concrete. The rebound hammer can be used on horizontal, vertical, or inclined concrete surfaces, provided a correction is made for the angle of inclination. Prior to testing, the rebound hammer should be calibrated using a calibration test anvil supplied by the manufacturer. Correlation of rebound number should be developed where possible with the strength of partially destructive core testing. like for example cylinders, cylinder strength results if they're available for the particular concrete mix. Rebound hammer testing should be undertaken in accordance with ASTM C805 test method for rebound number in concrete. And like other non-destructive testing, needs a bit of experience in terms of the execution and also interpretation of the results. And this sort of chart that you can see in this slide comes with the rebound hammer prepared by the manufacturer. As you can see, it can relate the impact rebound number that you can read out from the hammer to the predicted compressive strength depending on location of concrete surface to the hammer. Another use of non-destructive testing, especially for us in Australia, is where we need to know about some corrosive activity in a reinforced concrete. Majority of our bridges, roads and buildings are located in high corrosive areas, and monitoring the corrosion activity in these structures are very important. Corrosion of rebar is crucial to the expected life of reinforced concrete. More specifically, chloride-induced corrosion, where chloride ions penetrate to the surface of reinforcing bars, destroy the passive film and change bars from passive state into active state. The most famous non-destructive testing method for testing reinforcement corrosion is the use of a half-cell system and high impedance voltmeters. This test can be categorized as semi-destructive because the electrode will need connection to a rebar. So at the start of this test, you need to locate the rebars first and then drill into concrete in order to get connection to one of the rebars. The system is capable of detecting the current flow of ion migration through the concrete between anodic and cathodic sides by measuring the resultant equipotential lines. The concrete functions as an electrolyte here, and the risk of corrosion may be related empirically to the measured potential difference that leads to corrosion. On the left hand side schematic, you can see the concept of half cell potential testing using a voltmeter, and the fact that the potential is being measured between the electrode and the rebar inside. According to ASTM 876, you can interpret the results in this way: that, for example, 90% chance of active corrosion if negative potential is more than minus 350 MV, if negative potential is more than minus 350 MV, and 90% chance of no corrosion if the negative potential is less than minus 200 MV. And there is obviously an uncertainty area in between where the negative potential is between minus 200 to minus 350 MV. And this is what you can usually get from this test. This contour map shows you where the corrosion potential is higher, such as in red areas, and whereabouts you may have low risk of corrosion, like in green areas. This is a very good test and is carried out by a lot of engineers and asset managers around the country these days. But the main point is that the interpretation really needs to be done by an experienced engineer or a corrosion technologist. This test may be done from time to time to monitor any changes in the corrosion activity at different areas. Electrical resistivity of concrete is another indicator. Although there have been some debates on how to use these results of concrete electrical resistivity, there is a rule of thumb that can help with it. In general, the higher the electrical resistivity of concrete can mean the lower porosity and permeability and consequently better long-term qualities of concrete. In other words, when you see a concrete with low electrical resistivity, you might be concerned about that, specifically if it is located in a corrosive environment. Albeit this is a general statement and can vary from concrete to concrete. Surface electrical resistivity of concrete is usually measured based on the 4-probe Werner array technique. This test measures resistivity around the concrete specimen using 4 channels of 4-probe array located at 90 degrees from each other. Many people believe the electrical resistivity can be used to determine the chloride permeability of concrete in accordance with AASHTO TP 995 and ASTM standard. The measurement can be used for durability-based quality control of concrete as well as the service life design of concrete structures. Another non-destructive testing that is widely used is the cover meter. In most cases, this is actually the first thing to be used to locate the rebars and determine the cover of concrete before we do, for example, the half cell potential testing. The cover meter technique is the least complicated and least expensive of all the NDT techniques, based on a low frequency alternating magnetic field into the concrete surface. The presence of steel in this magnetic field induces eddy currents and a voltage change that can be detected and displayed by the meter. The cover meter has the ability to locate reinforcing steel and other metal objects. Also, it measures the depth of concrete cover and can estimate the size of reinforcing bars. The accuracy of a cover meter can be affected by the amount of steel reinforcement present, particularly by the amount of congestion and the presence of multiple layers or other metallic inclusions. Also, the cover of concrete can affect the accuracy of the results. Its accuracy can also be improved by calibrating against reinforced concrete with known dimensions and size of reinforcing bars. A cover meter is generally reliable to a depth of 100 to 130 millimeter and should be used by an experienced operator. Before we finish this presentation, I'd like to name a series of documents prepared by CIA. CIA's new Concrete Durability Series Z7 Recommended Practices is the one that I wanted to introduce you, especially because of the testing that they have introduced for the durability assessment of concrete. The CIA has published 3 new recommended practices as outcomes of the incredible hard work from the CIA Durability Technical Committee formed in late 2008 to review Z7 2008